you will find the work energy theorem on page 44, right in the middle of the page. The work energy theorem that you find there is a beautiful one, and it says the work done on an object by a net force F net is equal to the change in kinetic energy delta K of the object. Now, that is now the work energy theorem in words, and if you have to spot something for the exam, this is it. Please see that you know the wording of the work energy theorem. In formula, you will also find it on the data sheet under work energy and power, and I have now removed it from the data sheet just to get it a little bit larger that we can see very clearly what it is about. On the data sheet, you will see this equation that says W net, the net work, equals delta K, or you can also say delta EK. The point is that some people use K for kinetic energy and some use EK for kinetic energy. Whichever, you're welcome to use it. You've got a choice. And delta K, the change in kinetic energy, is the final kinetic energy minus the initial kinetic energy, or if you want to use that one, it's the same story but just using that one. Can we for today use K for kinetic energy so that don't need to do everything twice? So we are not going to look at delta EK, but you are welcome to use that. I'm just going to use delta K for kinetic energy. But this is it in a formula, and whenever you have to do a calculation where you have to use the work energy theorem, you have to start off with this equation. You are not allowed to use an equation of your own or one of your own inventions or whatever, any other equation that you've come across. You must use an equation that's on the data sheet, and this is it. This is the equation that's on the data sheet that's dealing with a work energy theorem. That is the formula. So if a problem states that you have to do a problem using the work energy theorem, first of all, you write down that equation after you have now done your picture or your vector diagram, your force diagram, but that is the equation with which you have to start. Now, I think we are ready now to do an example or two using the work energy theorem. And the best way to start, I think, is by looking at the question that was asked last year in the 2011 final exam paper, and it's question number 5 on page 11. Now the question reads, a rescue helicopter is stationary, it hovers above a soldier. So there's the helicopter, there's the soldier. The soldier of mass 80 kilograms is lifted vertically upwards, maybe we can just make sure we know it's upwards, through a height of 20 meters, so it's through a height of 20 meters, by a cable at a constant speed of 4 meters per second. So maybe we can write it there, 4 meters per second. The tension in the cable is 960 newtons. Assume that there is no sideways motion during the lift. Air friction is not to be ignored. So there is air friction. And while we are thinking about it, let's add it. If he moves upwards, in what direction is air friction going to be? Friction is always opposite to motion. So in other words, the air friction is going to be downwards. So the air friction will be opposite to his motion. He moves up, friction is down. Now, first of all, state the work energy theorem in words. We've done that, all right? Now draw a labeled free body diagram showing all the forces acting on the soldier. So in other words, we have to have all the forces acting on the soldier. Now, first of all, it's a free body diagram, and it's a free body diagram, so in other words, it's just a dot for the soldier. Now, what are all the forces acting on the soldier? In the first place, there is that cable pulling him upwards, And then the one that is always, always present, the gravitational force downwards, and the frictional force, which is also downwards. So these are the three forces that are acting on the soldier. And what should the labels be? Please note again that all of these labels must end on the soldier, on the soldier, on the soldier. So please don't write there tension in the cable, because the tension in the cable is a force in the cable. They didn't ask you for the cable, they asked you for a force on the soldier. So that is then the force by the cable on the soldier. Then this is the frictional force of the air on soldier. And this is then the gravitational force of the earth on soldier. Do you see that each one of these ends on the soldier? Right, and now they say, use the work energy theorem to calculate the work done on the soldier by friction after moving through the height of 20 meters. Use the work energy. Now the work energy theorem, you have to write down immediately what I said, that W net equals the change in kinetic energy. Now on that same page, they tell you that the change in kinetic energy is Kf minus Ki. Now, first of all, let's see what we have here for the net force. What is the net force? They ask you that you have to calculate the work done on the soldier by friction. So they want you to have the frictional force. Now the net force, let's first look at that. The net force, if we look at the sum of all the works, it will be then the different forces that act on the soldier will be the force by the cable on the soldier. So the net force will be then the force, the work by the cable. It will be the work done by friction. It will be the work done by the air resistance. So the work done by the cable will then be the force by the cable times displacement, cos theta. The work done by friction, well, that's what we have to calculate. We want to calculate that. And the force work by air is then the force by air, delta y, cos theta. Now, the force by the cable, they tell you that. They say that's 960. And the displacement, they say that is 20 meters. And now what we must now remember is that the displacement is upwards and the force by the cable is upwards. So the angle between them is naught. So that is then cos naught plus the work by friction plus the force by the air. Sorry, that is not the air. That should be the weight. Right, the weight will then be his weight, which is his mass times g, and delta y is 20 meters, and then cos theta, the space, I'm running out of space. Cos theta, the angle between the weight and the motion, remember now the weight is downwards and the motion is upwards, so that will then be cos 180 degrees. And now you can just calculate that. Now, in order to save a little bit of time, I'm now not going to do this calculation. You can plug it in onto your pocket calculator, but now you will see that you end up with that equation. But now the problem is I've got two unknowns here. I've got the net work, and I've got the work done by this one. So what now? Well, fortunately, I can use the work energy theorem. I actually have to use the work energy theorem. And the work energy theorem says that that is equal to the change in kinetic energy. So let's look at that. What is the change in kinetic energy? The change in kinetic energy is then half mvf squared minus half mvi squared. And that is then equal to the mass of the soldier is 80 kilograms. Vf is 4 meters per second. And the mass of the soldier is 80. And Vi is also 4 because it's moving upwards at constant velocity. So the velocity doesn't change. Right, so in other words, that and that is exactly the same. So the change in kinetic energy is 0. And because the change in kinetic energy is 0, the net force is 0. So in other words, 0 equals 960 times 20, and now you can just calculate what is the the work done by friction, by plugging in those values. Right, so that is then the question that was asked in the final exam last year. I would like to do an example on an inclined plane. Now, if this is an inclined plane, and I think maybe we can look at the example in the book on page 51. There's a very nice example in the book on page 51. If you've got a body on an inclined plane, and that angle is, for instance, 20 degrees. Now, if that is now the body, then what are the forces that body will experience? Well, the first one that we know, if they ask you to draw a force diagram for this body, and say now, for instance, there is friction, then what you will find is that one force that's always present is the weight acting downwards, the gravitational force acting downwards. But you see, what happens now is that force has got a component. You see, because we now want this block is going to slide up or down along the plane. We want to work with forces along that plane. And the weight is acting in that direction. But the weight has got a component in that direction and that direction. Now, fortunately, we are not going to deal with this one now. This is the one, the troublemaker. Now, you see, when we are working with an inclined plane, then we are now really working with a wicked example. Because you see what happens is this is a very naughty force. This one tends to pull things down an inclined plane. If you would, for instance, park your car on an incline and you forget to apply the handbrake, you're going to find your car right down there at the bottom. It will run down the incline. Why? Who is responsible for that? Nobody pushed it. It was this little one that is pulling it down. It's this component of its weight. And I don't want to do the maths now, but I want you to memorize. I promise you this is worthwhile. But this component is always the weight, whatever it is, sine that angle. Now, I don't want to write here sine theta, because then you might confuse that theta with the theta that you get with work equals F delta X cos theta. But that angle will always be this one, you see. So in other words, that component, I want you to remember, that is the one that sins, that's pulling it, the naughty one, that's pulling it down the plane. It's Fg, the weight, sin this angle. So you calculate that component. That is now one thing that you have to remember. If they ask you to draw a force diagram, I just want to show you that quickly. The force diagram will be, it's the weight acting on it, and then it is let's say there is friction, it will tend to slide down, so there will be a frictional force acting in that direction, and then obviously the plane is exerting a normal force, so the force will be at 90 degrees on it. That will be the normal force. Those are the three forces. If it's a free body diagram, the three forces will be this. Right, that is a free body diagram, this is a force diagram. You don't show the components here yet. This is now just to show all the forces acting on the body. But if you want to do a calculation, you are going to work with that. Then you ignore the weight, because that is the part of the weight that you are going to look at. And then there's the frictional force. The normal force isn't a problem at all. All right, so remember that is very, very important. Now, let's have a look at the example on page 51, where they say that you've got now this body on this 20 degrees incline. It's a 2 kilogram body, and somebody is pulling it upwards, applying a force of 20 newtons, and they're pulling it up the incline for 5 meters. And now they say that right at the bottom, the question reads, an object of mass 2 kilograms is pulled from rest up a ramp with an angle of inclination 20 degrees by a 20 Newton force. The ramp is 5 meters long, right, we've got that, and the box experiences a constant frictional force, let's put that in, of 3.3 newtons, because we know if it's moving in that direction, the frictional force is in that direction. Calculate the velocity at the top of the ramp. So what is the velocity there? So what we are going to do now is we are now going to use the work energy theorem. Look, you can use Newton's second law and equations of motion, but we are now dealing today with the work energy theorem. So if we use the work energy theorem, we first have to look at what is the work done by each one of these forces. What is the work done by that force? What is the work done by that force? And don't forget about the naughty one, the component of the weight, which is down this plane, which is Fg sine 20. You see, that is another force. So we've got the 3 forces, and we have to calculate the work done by the 3 forces if it's moving in that direction. So remember, displacement is in that direction, and now we have to look at that. Okay, so the net force will then be the force exerted by this Fg sin 20 degrees, and it will be the force exerted, delta x cos theta plus the force exerted, the work done by the 20 Newton, delta x cos theta plus the work done by the frictional force, which is the 3.3 delta x cos theta. Now, this one is then the weight is 2 times 9.8 sine 20, right? So you can calculate that, times delta x is then 5 meters, and then cos theta, you see this one is opposite to motion. This one is opposite to motion. So in other words, that will be then 180 degrees. Plus, this one is then the 20 Newton force. The displacement is 5. And the 20 newtons is in the direction of motion. So in other words, it will be cos 0. Plus, the last force is 3.3 times 5. And once again, the 3.3 is opposite to motion, so that will be cos 180. Now, if we look at these, then you can just multiply that, and you get the total. But now, how do I get now what is the speed at the top? When you've got now the value for the net force, which works out on it's 100 minus 33.516 minus 16.5 as they've got in the book, then you can say, but the net force equals half mv squared plus half mvi squared. Now we've worked out the net force, we've got that, and the mass of the crate is 2 kilograms. The final velocity is what we want to calculate, and the mass is 2 kilograms, and the initial velocity, they said, is 0. And then you just solve for v, which should work out on 7.07 meters per second. I'm sorry that I couldn't do the actual calculations, but I think if you've got the idea as to exactly how to do the calculations, I think that is more or less what is the difficult part. But you can punch in these values onto your pocket calculator to just get the values. But the important thing is, remember that component of the weight, the FG sine theta, where theta is not the same theta as the one that you get in the work formula, the W equals F delta X cos theta. It's not the same theta as that. This is the incline, the one that you've got in the sine theta. Remember that one, and then the rest will be exactly the same as before. And until next time, good luck and God bless.